Synthesizable random test bench for multimedia IP verification. Abstract. Constraint random verification is effective only when a sufficient number of random tests are performed. For multimedia IPs, which have thousands of configuration parameters, the required number of tests outweighs the capability of simulation-based verification. Although FPGA or emulation technologies have the potential to resolve this problem, the expertise gap between simulation and FPGA is another problem to be addressed. In this paper, the author presents a synthesizable testbench architecture that is based on a test instruction set core TISC, which is a process core with the instruction set specialized for test program, and synthetic memory SynMem verification IP, which behaves as like an AXI-based memory model implemented without the physical memory devices. Since the testbench is an isolated system without interaction with outside world, it guarantees perfect reproduction of found issues over multiple verification platforms, including simulation, emulation, and FPGA. Chapter 1. Introduction. Multimedia IPs such as image signal processor, image scaler, and display processing unit have thousands of parameters for calibrating image quality, power consumption, and processing time. The constraint random verification has been the primary way to achieve the functional coverage goal of such hardware designs. Recently, however, the author faced the situation that the millions of random tests were required to cover immense coverage space. Considering time allowed to verification engineers performing such a large number of tests by simulation was impossible. The author resolved the problem by developing random test bench to be synthesizable so that they can be run by both simulation and an FPGA. The demanded synthesizable test bench should be isolated system which does not have any interaction with the outside world, so that it enables the perfect reproduction of issues in different execution platforms, including simulation, emulation, and FPGA. Minimizing data transfer between the host machine and the FPGA board is also highly demanded to maximize the throughput of FPGA-based regression tests. The figure 1 shows 3 different testbench architectures with their own pros and cons. So in this simple testbench architecture shown in figure 1a, a few essential components are integrated with the design under verification DUV. So the test program, which accesses DUV, verification IPs, and SDRAMs to control overall the behaviors, is written in C and C++ language and executed in both host machines. In this architecture, the test program accesses to the component inside of FPGA board through the USB or PCIe link. Although it looks simple and easy to develop, the test program wasted considerable time for accessing thousands of configuration registers of DUT and transferring data to or from SDRAM device. So this kind of test bench is not adequate for massive regression tests, which should perform the several millions of tests in a few days. Moreover, reproducing issues by simulation often failed because temporal behavior of the USB link can be neither controlled nor modeled accurately. And this situation happened. The verification engineer should spend considerable time to root cause of the issue, performing various experiments at FPGA level. So figure 1 shows an alternative architecture in which the test program is executed a microcontroller embedded in synthesizable testbench. After the test program binary and test vectors are downloaded, the microcontroller governs overall behavior of verification IPs and DUV. So the above-mentioned problems are no more exist in this test bench. Instead, however, new problems arise such as a slower simulation speed, increased complexity of test bench maintenance, and more different debugging of the test programs. So many simulation technology based on verification engineer, hereafter DV engineer, do not want to observe such difficulties in their DV test benches, which are already complex. In this paper, they also present a novel test bench architecture shown in figure 1C, which is based on a test instruction set core TISC and synthetic memory SI and MEM VIP. TISC described in section 2 is a processor core with an instruction set specialized for test program description. The SynMem described in section 3 is an AXI slave interface implemented with real memory devices. In section 4, the test program generation flow and several test case studies are explained. Finally, conclusions are discussed in section 5. The figure 1 is various synthesizable test bench architectures. Section 2, Test Instruction Set Core TISC. Inventing a new instruction set architecture ISA and implementing it require considerable effort and time. Knowing this very well, however, the author had decided to make a new processor core because most of DUV engineers felt difficulties in integrating conventional embedded process cores in their test benches. The common reasons were they are not familiar with writing and debugging C and C++ based test programs. About half of engineers wanted to concentrate their time in system-level or UVM-based verification instead of a C-based embedded software development. Another bunch of engineers claimed the slower simulation speed and inefficient debugging would take more verification time. All of engineers commonly complained that they cannot manage two different test benches. One is for simulation-based constraint random verification, DV test bench, and another is the synthesizable test bench for massive regression at the same time. The author had thought that way hiring more verification engineers to take a full charge of FPGA-based massive regression testing, including the synthesizable test bench development. After a shorter mental simulation of this idea, the author had abandoned it because the domain knowledge about the multimedia IPs is the most important ingredient for successful test development. The DV engineers already have the domain knowledge, but sharing it with the newly hired engineering is too expensive or impossible in short verification time. So the author had tried to find a way to DV engineers feel free to adopt it. The author realized the clear separation of expertise of DV and FPGA engineers by specialized processor core TISC. This section described about the processor and its real benefit is explained in section 4. A. Microarchitecture. Figure 2 shows a block diagram of TISC. It provides an APB slave interface through which external hosts can download executable program data into internal program memory. After the external host gives a start command, the TISC executes instructions stored in the programming memory. The host waits for an interrupt request from the TISC and read the status register to identify result of the test. For simplicity, the TISC is based on the 3-pipeline stage architecture. So address generation unit calculates the addresses of program memory for fetching instruction code. Decoder unit decodes the instruction code and decides control values for the processing element in the execution stage. The execution stage consists of several processing elements. At the center of it, arithmetic logic unit ALU, multiplier divider unit MDU, and the compression unit XSHIT. An ALU is a combinational logic that performs addition, subtraction, and logic operation with two 32-bit input and one 32-bit output. So MDU, multiplier divider unit, is a sequential logic that performs the shift, multiplication, and divide operation. Considering the multiplications and the divide operations are real in test programs, both operations are implemented in a special manner with the shifter and the ALU. The MDU in test program, the MDU accounts for only 1,762 gates. In a test program, majority of the instructions are configuration register write operations, so thus TISC provides a special instruction to compress a sequence of register accesses. The compression unit translates in the encoded binary stream into the original sequence which flowed through the external interface unit, such as a PB masters and programmable I/O unit. The core provides a total 32 registers of 32 bits wide, which are divided into two groups, general register and special register. The general registers could be accessed by all instructions, while the special register could be used by specific instruction. Such partitioning of existing registers is to reduce the complexity of two read and one write register file structure. The figure 2 is a microarchitecture of TISC. The condition evaluator decided conditional execution of instruction referring to one of 32 general flags. A 32-bit general register R11, event from a programmable timers, event from a programmable I/O unit. The instruction-wise conditional execution is similar to ARM instruction set architecture, which allows only 4 conditional flags. Rich set of conditional flags of TISC allows a test program to be implemented, minimizing conditional branches that makes the follow of the control to be linear and easy to debug, especially for hardware verification engineers. Programmable I/O unit is preferred for direct signal level communication with outside of the core. The unit consists of event activators EA, event receptors ER, general handshaking masters GHM, and general handshaking slaves GHS, whose types and values are controlled by instruction and registers. EA and ER are both the 64 bits wide. Among 64 bits, a half of them is mapped to general registers so that the path units can access them directly. Another half of them mapped to the special registers, which can be accessed by special move operation. The I/O unit could be programmed to interact with the DUV flexibly. For example, the interrupt request from DUV could be connected to the power of ER. A triggering signal to DUV could be connected to one of the EA, It is also possible to implement 32-bit AXI interfaces with 3 channels GHM, 2 channels GHM, and parts of EAs and ERs. Programmer timers used to generate periodic or random tests in a test program. A timer is associated with a special register, say timer X. If non-zero value is written to this register, the timer decreases the value per cycle and generates event when a value becomes zero. The periodic events are generated by writing a constant values to this register, and random events are generated by writing random values. Another source of the randomness is the random number generation network (RGNet), for which one general and one special registers are mapped. By using RNGNet appropriately, the size of the test program can be reduced greatly. Details about RNGNet are described in separated subsection in this paper. TISC has APB masters to support separated address spaces for DUV and verification IPs. The APB master for DUV provides 2 special features for powerful verification. Checksum calculators observe the read transactions and automatically calculate the checksum of the data from the DUV. The output of a calculator is mapped to initialized, cleared by assigning 0 to map to general registers. This feature is effective for checking DUV, which have many register mapped output. Another special feature of the APB master for DUV is a random delay insertion between transactions. This feature is enabled by setting a special register, APB RNG, with 32-bit value whose lower 16 bits are taken as a random seed, and most upper 16 bits are used as a maximum delay. For each APB accessed, the lower 16 bits of this register are updated by a pseudo-random number generator, PRNG. So the clock controller generates a clock-enabled signals for DUV and VIPs to hide unintended delays due to the multi-cycle instructions, such as multiplication and division. Another usage of this feature is turning off the clock of the DUV while VIPs are being configured. The external host can selectively enable or disable this control. B. Instruction set architecture. Figure 3 shows the format of the instruction code. The MSB bit of the first byte of instruction specified whether the instruction is conditional or unconditional, and the last 7 bits are operation code, OP code. If it is conditional, 8-bit condition code is followed by the OP code. Depending on the OP code values, variable length operand bits are followed, whose format is shown in figure 3b. Total 28 operand formats existing, including the operand. The variable length operand bits composed of constant, register, shift amount, and extended OP fields. The length of the constant field is a variable from 4 bits, denoted as C4 in the figure, to 32 bits, denoted as D32 in the figure. Constant field where length is more than 16 bits are encoded in the little endian notation to simplify multiplexer logics of decoder unit. A register field is fixed as a 4-bit length which can discriminate up to 16 registers. Depending on OP code value, each interpreted as a general register, special register, and general flag. Some of operand formats contain a 4-bit OP code extension, which is appended to the original 7-bit OP code to form total 11-bit wide extended opcode. All of arithmetic and compare instruction take these operand format. Unconditional instruction with no operand is 8-bit length, which is minimum length, and a conditional instruction with 232-bit constant operand OPR underscore FMT 15 is 80-bit length, which is maximum length. Multiple IPs provide many configurable parameters which allow for trading between image quality, performance, and power consumption. For example, the Bayer image processor ISP of a mobile application has a totally 9,209 user configurable registers as listed in Table 1. So test program should write all of these registers at least once. Thus, majority of instructions be described and executed for a test are register accesses through the APB masters. Considering this nature of the test programs for multimedia IPs, TISC provides special instruction to implement a sequence of register accesses efficiently. So the figure 3 instruction format of TISC. Duty underscore write is a pseudo instruction that writes a value to a specific address through the APB masters. This pseudo instruction could be mapped one of actual instruction with different operand formats. The mapping is performed by TISC assembler. The default encoding of this pseudo instruction is operand from OPR underscore FMT 15 has 232-bit constant field. More bit efficient encoding choices are made as follows. For address field, the immediate value or differential from the previous instruction could be encoded as 8-bit, 16-bit, and 24 bits, with assigning the different OP code. If the address is increased by 4 from the previous instruction, OP code that represents the auto-incremented address field is selected, removing the address field. If consecutive instructions write to the same address, the group of instructions is replaced with an instruction representing repeated address field. For write data field, the special OP code for zero write values is reserved, considering as well as the above encoding schemes. So for write data field, a register could be specified instead of a constant value. 3 operand format, OPR underscore FMT 16 to OPR underscore FMT 18 are reserved for this case. For APB write, the pseudo instruction DUT underscore write underscore RND, which takes one of 2 outputs of RNG net as write values, is defined. The output of RNG net be referred is specified by the OP code, so only one constant field to represent the target address is required from OPR underscore FMT 0 to OPR underscore FMT 3. For repeated or incremental addresses, the constant field represents count of repeats instead of the address. DUT underscore read is a pseudo instruction that reads a value from a specific address through the APB master. Basic operand format is one constant and one register field from OPR underscore FMT 16 to OPR underscore FMT 18. Similar to the write, it could be mapped one of the actual instructions with different operand format, and the same compression schemes are applied to the address field. The register field, which specifies the index of register to which read data will be stored, the register field could be omitted. In this case, the read data is used by the checksum calculated in figure 8.1 to be used for output checking. DUT underscore read underscore test is a variant of the DUT read, which has one additional constant field with which our read data is compared and raise predefined flag upon mismatch. TISC supports conventional ALU and MDU operations such as add, sub, and, or, not, merge, and divide. It also compares operations which set one of general flags. It sets logic not operand not. All of these instructions take three operand fields. The one field is target register or flag to which the result will be stored and rest are input. One input is always a register and another can be either a register or constant. A constant field can be encoded as 4 bits, 12 bits, and 20 bits, and 28 bits, and 36 bits, including 4 bits, 0 padding. Depending on the least significant 3 bits of the OP code extension field, so if the extension of 4 binary 0004 bit binary 0000, the constant field is a 4 bit constant value. If the extension is 4 bit 1000, the 4 bit constant field represents an index to constant table which holds 16 constant values frequently used in the multimedia test programs. According to the extension field, 12 bit and 20 bit constant field could be divided into shift amount bit and shift target bit. This idea is similar to ARM ISA, except that the TISC supports variable length immediate field and 4 bits shift amount, while the ARM supports 8 bits immediately field and 4 bits rotation mount. Arithmetic instructions cannot take special registers as their operand indirectly. Instead, TISC provides MOV instruction which can copy values of a register to another regardless of whether they are general or special. Load and store instructions are supported to read or write data from or to the program memory. So since it is a 3 pipeline stage von Neumann architecture, accessing the program memory by a load and store instruction takes 4 clock cycles, 1 cycle to change SRAM address, 1 cycle to read SRAM output, 1 cycle to pass through the code stage, and 1 cycle to finalize the operation. This limitation, which is not accepted for conventional software program, is no big deal in TISC-based test programs because those instructions are seldom used. This configuration register-related information is encoded in the program memory with the specialized instruction. Input data for DUV are randomly generated by synthesizable verification IPs. The output data of the DUV are checked by comparing checksum, where the reference checksum values are hard-coded in the constant field of compare instruction. Although 16 general registers are defined, 5 of them have special usage and only 11 general registers could be used for general purposes. So TISC supports the hardware controlled stack operations push or pop, which saves or stores register values to or from normal memory. From program memory. The initial stack pointer is always 65,536, which is the bottom of the program memory, and auto-increment or increment by push or pop, respectively. Current stack pointer is mapped to a special register, STK, and accessible by MOV operation. TISC supports the three-branch instruction jump, call, and return. Jump could have either an 8-bit signed constant direct branch with a relative offset, a 16-bit unsigned constant direct branch with absolute address, and a register in direct branch with the absolute address field. Call is the same as jump except it stores the return address in special register. Three 16-bit register, a special register, RET0, RET1, and RET2 are reserved for call. If the branch is taken by this instruction, value of RET1 is copied to RET2 and the value of RET0 is copied to RET1, as well as the program counter PC of the next instruction is copied to RET0, so the return performs copies of in the reserved direction to the jump to the next instruction of recent call instruction. Thus, TISC supports nested calls up to the 3 levels, which are generally enough for the test programs. Figure B2 example codes of the same functions implemented using the different instruction. Figure 4 is 3 ways to implement conditional execution. Figure 4a is conceptually C-code read 2 registers of DUV and perform the proper actions based on the read values. Figure 4b is just assembly code of this example function implemented with the conditional flag. The instruction EQ set to general flag F1 if the value of a register is constant, the value are the same. In this code, F1 and F1 denote that the instruction should be executed if the general flag F1 is true and false, respectively. Figure 4c and figure 4d are assembly codes implemented with jump and call instructions, respectively. The encoded program sizes of 3 implementations are 56 bytes and 70 bytes and 80 bytes, respectively. The conditional instruction is more size efficient than the jump and call because more duty_write instructions are linearized that result in better address and data field compression. For the repeated condition field, TISC provides the instruction skip, which ignores number of followed instructions. The TISC assembler automatically inserts skip for consecutive conditional instruction with the same condition, eliminating repeated condition field. So using conditional instruction instead of the jump and call is always a size optimal choice. The number C is Random Number Generation Network, RNGNet. For verification of multiple IP, which has hundreds of configuration registers interrelated with each other, constraint and random verification technique is crucial tool to cover wide and complex verification space. This is the one of the reasons for adopting system Verilog. Hundreds of configuration registers mean the test program should contain at least the same number of hundred and data. Considering the 64 kilobyte program memory and compression of address and data, TISC can support thousands of configuration parameters, which count is much larger than the count of configuration registers of conventional multimedia IPs. Unfortunately, however, this is true only for the test program that execute just a single configuration. In real world, the running multiple configurations for different contexts, that is, the images from different image sensors. In the frame or line, interleaved manners is required. To cover such cases, a test program should hold several sets of configuration values could exceed 64 kilobyte size limit. One simple solution is increasing the size of the SRAM. Some FPGAs provide block DRAMs whose total size is several megabytes. However, the author prefers to keep current 64 gigabyte limitation for simplicity of the instruction set architecture. To encrypt the program memory, registers and constant fields that are related with the address of the program memory such as PC, RET0, and branch target should be enlarged. So the author had tried to find a way to use the program memory more efficiently and found solutions was generating the random values at runtime. In constraint random verification, configuration registers of designers models as a random variable with constraint. The sum of random variables has a complex and interrelated constraint that requires constraint solver for quality of generated random values. Registers that represent the width and height of the input images are such registers. Fortunately, not all random variables have complex constraints. For example, base register address of the direct memory access DMA could be generated with a simple pseudo-random number generation algorithms. Random number generation network RNG entity in figure A1 is embedded preferred that generate random numbers considering user-specified range of values, distribution, formatting, and dependency with previous values. Figure 5 is the block diagram of a random number generation network, which is a network of user configurable components. The most important component is a pseudo-random number generator, PRNG, which has 3 inputs, seed, init, and active, and one output value. The input seed is the initial value of a pseudo-random number sequence. 1 bit input init resets internal state of PRNG to restart the sequence. The output value is current random number, which is updated or remained depending on the values of 1 bit input active. RNGNet contained total 18 PRNG components. 8-bit PRNGs shown in the middle of the figure 5 are generating the random values. Outputs of them are clipped to the fit in the range of values configured by users. The figure 5 is a microarchitecture of a random number generated network RNGNet. After 4 clipped random values are logically shifted and concatenated from formed 32-bit values, this operation is performed by a component named concat in figure 5. 2 concats make 2 32-bit random values. Selector is a component that randomly selects one of the 8-bit random values. The dedicated 3-bit PRNG equals just to select one of the input randomly. There is a 32-bit address adder which takes up of a concat selector as its input. Another 32-bit adder sums up the result of former adder and the values of register base. The user can configure the register either to hold constant value to generate a random sequence with a constant bias or to save the previous values of RNGNet to generate a random number sequence which had dependence with previously generated numbers. The output of add is post-processed by a clip component and finally reached to the general purpose register R12. So the when an instruction refers to R12 as its operand. When an instruction refers to R12 as its operand, active signals of or PRNG can be high. Some tests require sequences of 32-bit values which contain both high and low frequency components. Such sequence could be synthesized by adding a sequence whose values are changed for each of a cycle into another sequences whose values are occasionally changed. To support some random sequences, the active signal to 8-bit PRNGs are randomly generated as follows. There are 8 30-bit PRNGs. The output of a 3-bit PRNG is connected to activators, which determines whether a 3-bit random number exceeds user-configured threshold. At the input of each 8-bit PRNGs, a multiplexer that selects one of the always changes to 8-bit outputs of activators. 3-bit PRNGs also have the same multiplexer structures for their input active. The figure 6 is an example how to configure RNGNet to generate lookup tables LUTs for gamma functions. The LUT is a mapping from 10-bit input pixels to 14-bit output pixels. For area efficiency, the LUT contains a mapping of 256 mappings and the rest 768 mappings are interpolated with adjacent mappings. So it was required to generate a random sequence of 256 elements. So one important constraint for the sequence is that it should be monotonically increased. Figure 6a is a simplified network of components to generate this random sequence, as well as random seeds. The initial values of base and minimum and maximum values of click are those controllable by a test program to exercise different cases as shown in figure 6. In fact, a simple network can generate simple curves, which is not easy to cover corner cases well. Alternative, the more complex network is shown in figure 6, where two random values as value sequences of different update frequency are generated and summed up to generate a more complex cover as shown in figure 6d. If the LUT is generated by a system Verilog and coded as a sequence of a DUT_write instruction, L is 520 bytes, 256 bytes for OP code, 4 bytes for the first address, 4 bytes for the first element, and 255 bytes for encoding differences of the last element are required. If the RNGNet is used instead, only 27 bytes are required, 24 bytes to compute the RNGNet, 1 byte for the OP code to represent a repeated DUT_write, 1 byte for the repeat count, and 1 byte to represent R12 as its operand. This figure is a figure 6 RNGNet-based gamma LUT generation. D is case studies. Table 1 shows the number of configuration registers of representative multimedia IPs. The registers are classified into two categories: registers related with the request interrupt, internal clock gating, and software reset and job management are categorized as system registers. Data processing registers, which are registers that have influence to the data flows and output data values, are further divided into registers with a simple constraint, hereafter simple registers, registers with a complex constraint, hereafter complex registers, and LUTs. For register write accesses, variable length encoding of the DUT_write instruction could reduce the size of test program binaries to 13% to 30% of the fixed length encoding cases. For LUTs, however, variable length encoding is not so effective. First, some LUTs have random values which have little chance for differential encoding. The LUTs for constant radial anti-shading function in Bayer image processor is such as the case. The LUT contained 32 by 25 total 800 elements. Gains, which can have arbitrary 12 bits assigned fixed point values. Another reason is that some LUTs have too many elements. Table 1 is configure registers and test program sizes of multimedia IPs. For example, the UI composer contained gamma LUTs for high dynamic range HDR, which have a total 1,596 entries that require at least 7 KB, even considering differential encoding. For such LUTs, employing the RNG-net could be helpful. Figure 7a is an example how to save a lot of program memory size, replacing a sequence of DUT_write instruction with a single limited operation that takes R12, the register that mapped to RNG-net as its operand. For register and read accesses, the automated checksum calculation was used to simply output checking sequence. PDAF accelerators reads phase data stream from an image sensor and generates various statistical information that is used by autofocus AF software. This statistics information consists of 1088 words, 4342 bytes, 52 bytes, and stored in an internal SRAM of an accelerator. This software can read the information by reading a specific address, hexadecimal B04, repeatedly. Figure 7b shows how to check the validity of this information by using single instruction. In this example, the instruction DUT_read_RPT performed the read access to the address hexadecimal B04 for the 1088 times. The checksum calculator that decided nearly 2 APB masters for DUV, shown in figure 2, automatically generates checksum of the read data that it is compared with the reference checksum values to determine whether the output is matched or not. As listed in Table 1, the sizes of test program binaries do not exceed 32 kilobytes, which means the current 64 kilobyte limitation of program memory of a TISC is reasonable. In the image scalar verification, the author's team performs totally 100 million tests to cover all possible scaling ratios. Even if the variable length encoding is applied, the total size of the test program exceeds 600 GB, which is not a trivial capacity. The TISC instruction set architecture could be implemented as an interpreter running on a classic microprocessor instead of implementing the custom process core. In this case, the many building blocks such as RNG-net, programmable IOs, and a checksum calculator should be implemented as a software, which slows down the simulation speed, or as a separated flip-flop hardware, which complicates the debugging of the tests. In fact, the author had tried this approach before implementing a new process core. This attempting had failed because most DVA engineers spend too much time in debugging test programs. Although implementing a custom processor had taken considerable time and effort. The engineers prefer this solution because all of the state variables, including the TISC core, could be observed and analyzed by a single waveform which is familiar to them. Figure 7 TISC codes in a real application. Section 3 is synthetic memory verification, SynMem verification IP. The recent multimedia IPs for mobile APs support the 36-bit address space, which means that the testbenches also should support very wide memory space. Conventional solution is integrating an NMU in a testbench, which increases the complexity of debugging issues greatly. The time to download and upload images also matter. The size of a bare image of a 200 megapixel image sensor is 240 megabytes. Downloading it into FPGA via USB link takes several minutes, which overwhelms the actual test time. As noted previously, employing SDRAM in a test bench makes the exactly production of issues by simulation impossible. This implies that some amount of time and manpower should be reserved for a potential issue debugging with the FPGA board. Some multimedia IPs having multiple AXI master interfaces. The test bench should include an AXI bus fabric to connect multiple AXI masters to the single SDRAM controller. In this case, however, the behavior of all AXI masters become interrelated and equality of verification could be limited. The above problem is the requirement for a new solution supporting wide address space without MU. Downloading and uploading imaging data are not required, guarantees perfect reproduction of issues by simulation, and multiple AXI masters are serviced independently to each other. In short, the mission is implementing verification IPs with an AXI slave interface which behaves as like an unbounded memory component without any real memory device. Synthetic memory VIP, SynMem, represented in this section is that solution. A. Microarchitecture. Figure 6 is the block diagram of SynMem. It has one AXI slave and one FPGA slave interfaces. Address requests through the read and write address channels on the AXI slave interface are stored in read request map RRM and the write request queue WRQ respectively. Although both RRM and WRQ are implemented in the small-sized SRAM, their access behaviors are different. Any element of RRM which specifies information about the read transaction could be accessed by each index. So each name is a map. Random selector select one of the available elements in the RRM to be responded to the DV through the read and data channel of the AXI slave interface. WRQ is a queue which provides output to the first in, first out, FIFO order. This simple behavior is enough because all of the AXI master interfaces of multimedia IPs do not allow the write data interleaving. For the last write data, the write ID is pushed into write response map WRM. Similar to RRM, a random selector selects one of the available ID and pops from the map and responds to the DV through the write response channel of the AXI slave interface. The ready signals of the read and write address channels are driven to the low when RRM and WRQ are full, respectively. Additionally, those ready signals and valid signals of the write response channels are driven to the low randomly. The user can control the random latency behaviors of respective channels by setting configuration registers. For random selection of random latency insertions, a set of pseudo-random number generators exists. Now, two key components, read data synthesizer and write data checksum calculator, remain to be explained. Figure 8 is microarchitecture of a synthetic memory, SynMem. B. Read data synthesizer. Since SynMem doesn't have any memory device, all of the read data to be returned to DUV should be generated internally and dynamically. The solution is adapting the hash function that returns a bit value via given 32-bit address. The hash function of a SynMem should satisfy three hardware requirements. First, it should be implemented as combinational logic so that it does not introduce additional cycle delays in the test. Second, it should not be the critical path of the entire synthesizer system. Third, impacted the total area should be negligible considering that 16 instances are required to SynMem. Exclusive word-based hash functions were featured to this requirement. Address to data spreader ADS is a group of 16 exact hash functions to generate 16 bytes from a 32-bit addressable value. The read data returned to a SynMem should model the characteristics of data streams for multimedia IPs, so the random values generated by ADS could be manipulated by predefined operation layers as shown in figure 9a. Different operation layers could be selected for different IPs for UI composers, which blends the pixels of multiple UI's image layers. Pure random numbers of ADS are enough for functional verification. For a motion estimation engine, on the other hand, adopting a 3x3 filtering is helpful to cover more functional coverage. The figure 9 is a read data synthesizer and its examples. C. Write data checksum calculator. Since SynMem does not keep the data, either the test program or the design itself cannot read back data written to the design before. So the memory VIP cannot be used for design which temporarily writes some intermediate data into memory and reads back later. For such designs, adopting SRAM instead of or as well as SynMem is inevitable. We can mitigate this limitation by taking the boundary of design for massive regression appropriately. For figure 10a is a conceptual system for clear exploration. A design IPA writes its output into a memory region, buffer AB, and another design IPB reads the content stored in the memory region. If we take the IPAB, which is a union of the AP and the IPB, as the boundary of FPGA-based massive regression test, a real memory is required for buffer AB. Instead of we take IPA and IPB as separated boundaries, reading back written data is not required. For up-checking the without a physical memory component, comparing the checksum of the data written by DUV with that the reference model is some way. Some multimedia IPs write data in a certain order, such as a raster scan order. In this case, conventionally, cyclic redundancy check CRC could be used. Unfortunately, however, some multimedia IPs write data in non-deterministic order. In this case, it is impossible to apply the CRC-based checking, so a new checksum, which is order independent, is needed. The author observed that the accumulated value of a write data stream is not bad as a checksum. By the virtue of associative law of condition operation, the final result is now related with the order of writer accesses. The pure accumulation cannot detect writing errors more than expected, so it also cannot detect writing expected data to unexpected address. The solution is watermarking the write data with a true address value. So figure 10 shows the structure of the checksum calculator. For each byte lane of W data and 32-bit checksum is calculated. The first step, expanding the original 8-bit data into 32 bits to prevent the zeros are added to the checksum, some of which are inverted. Then the extended 32 bits are XORed with the address bit so that the pair of address and write data are reflected in the checksum. Since exclusive operator obeys the associative law, however, the accumulating them cannot detect the case that the two write data are swapped and interchanged. To detect such a case is followed by a rotation operation, which takes the lower 5 bits of the address as amount of the rotation. This enables data swaps in a 512 byte address region could be detected. Figure 10 is testbench architecture with SynMem. The sum multimedia IPs write a single image data using multiple AXI masters such as IPC in figure 10, and implementing the synthesizable testbench. Two options are available. One option is using a SynMem and the bus batteries, and another option is attaching the individual SynMem instances to respect the AI semesters. As noted earlier, the former option makes temporal behavior of two ASI methods to be interrelated, so the latter option is better. So note that the test program can get the final checksum values via adding a partial checksum of both the SynMem instances. A simple restriction exists for the DUV, which write the data to the same address multiple times. Unfortunately, most of the multiple IPs for the imaging process write data only once to minimize the traffic to the external SDRAMs. Section 4 is adoption in real project. The purpose of the Synthesizable testbench is not to replace system value-based testbench. Simulation-based testbench, here after DV testbench, is still the primary environment to cover all of the verification scenarios. Synthesizable testbench is a supplementary environment for massive regression tests by either Emulation or FPGA to detect the corner cases whose detection probability is extremely low. Figure 11 shows the flow of the TISC-based test program generation, which is based on the intermediate output of the DUV testbench. So the instruction set in architecture presented in section 2 is to realize and maintain this flow and minimal effort, and DV testbench part of code to generate input image and analytics should be modified to model the synthetic memory VIP and RNGNet. The simulation testbench executed stopped after configuration register write and before starting the DUV. At this phase, the sequence of configuration register accesses and reference data from the reference model are available. Since the simulation stopped without running the actual design, it takes a few seconds. Repeating these steps with a different random seed, billions of low test configurations could be generated in a day. A simple script reads the intermediate configuration data generated from the UV testbench and generated TISC assembly code. The set of the binary code called as a TISC test TB is released to the FPGA exporter who integrated the synthesizable testbench, synthesizable the testbench in the FPGA board, performed massive regression, and report failed to test to the DUV engineers, which were reproduced by simulation for debugging. The key point of this flow is clearly separation of DUV and FPGA emulation engineers. All of the DV engineers are familiar with the FPGA emulation technology. Some of them feel strong technically and mental difficulty to enlarge their skill into this area. And this in the same for FPGA emulation engineers who do not have enough domain knowledge about DUVs. A contrasted solution is a new verification methodology represented in this paper. For DB engineers, modify the simulation testbench to generate true test configuration data, and writing a script to generate test code takes only several hours. As for the same FPGA and emulation engineers, so both groups of engineers still can show the best performance as they stay in the area of their own expertise, which enables the first massive regression be ready in a single day. Figure 11 is test program generation flow. The perfect of the reproducibility of the presented testbench architecture is another important reason for the success of this methodology. Once a failure found in the massive regression test, the FPGA emulation engineer can fire and forget it. The DV engineer, who has the ability to root causing the problem, can reproduce and analyze the issue with a simulation-based testbench. In fact, it's possible that an issue found in a massive regression test is not reproduced in the original DV testbench because the temporal behavior of it could be different from the TISC based testbench. In this case, DV engineer can simulate the TISC based testbench whose temporal behaviors are exactly the same to the FPGA or emulation. The TB engineers can analyze this issue and this environment comparing with the original testbench. Still no technical support from the FPGA emulation engineers required. Figure 12 is the trend of the adoption of the FPGA-based massive regression and verification multimedia IPs. Before the TISC, the 3 FPGA engineers can handle up to 2 multimedia IPs, spending most of their time to debug test code. In 2010, the same number of the engineers undertook the total 12 multimedia IPs concurrently. DV engineers can save their time by finding corner case bugs that much earlier, which reduce the number of iterations of simulation-based regression tests. Table 2 shows the recent corner case bugs found by the representative testbench and require time to detect them by simulation. Figure 12 is trend of adoption of massive regression test. Table 2 is recent corner cases found by massive regression test. So the chapter 4 is conclusion. While leading the multiple IP verification team for 10 years, the author often faced with the situation that a constrained random testbench would develop completely, but the number of tests siege with it was not sufficient to hit the corner cases of extremely low probability. The most of the DAUV engineers write verification plans reflecting the resources available to them, although they also wanted to increase total count as many as possible. The count of defined tests were always restricted by the amount of computing resource for simulation and available time for verification, which are always not enough. The synthesizable testbench based on a TISC and a synthetic memory VIP has migrated this problem. If a DV engineer spends a few hours to modify the DV testbench, he or she can generate millions of tests in a day. The FPGA emulation engineer also can finish the first massive regression test without feeling any burden to understand IP-specific information. Both engineers can stay their comfort regions in which engineer performances could be maximized. A designer's randomly verified means that some of cases were not exercised in the verification. To compensate this limitation of random verification, DV engineers define functional coverage models. However, it can mitigate but not resolve the limitation. An indisputable solution is testing all possible cases for which cost and time are matter. With the representative solution, the author is trying to change the multimedia IP verification paradigm from random to full combination. Today I read this paper, Synthesizable Random Testbench for Multimedia IP Verification, of the DVCON. Thank you for your time. See you next time.